All right, so I was at the grocery store yesterday and I came down the aisle with the tuna fish, canned tuna, and we see this brand called Safe Catch. They talk about how it's the lowest mercury limit of any brand. Wow, I don't remember ever seeing that brand before. I don't remember ever seeing anybody mention the mercury content on a food product. Interesting, right? Um, a lot of us might recall, especially if we go back 15 to 20 years, there was a big conversation around mercury contamination in seafood. Things like tuna, mackerel, any big predatory fish was a problem. Shellfish was another issue because these organisms had a tendency to accumulate mercury as they, lived in the aquatic environment. And a lot of us might be wondering, like, where's this mercury coming from? Like, why do we have to worry about mercury? If mercury is so toxic to people, why is it in the environment? Where is it coming from? So, of course, the FDA, Food and Drug Administration, published limits, recommendations on consumers as to they recommend you consume no more than a certain quantity of these foods, you know, in a week or month or whatever it is. And that was kind of the guidelines. We even had states where they told recreational fishermen that you should limit your consumption of fish from these waterways because we're concerned about mercury. And of course, the story of how that mercury gets there is really just a case of what we call bioaccumulation. So mercury gets into the environment through a whole possibility, a whole bouquet of pathways. Everything from something as basic as a volcanic eruption, right? That's a natural source, to air emissions from industry, to mining, where they used mercury as a way, especially in gold mining, to capture gold from ores, to certain industrial processes, especially historically, that used mercury as a catalyst, used mercury as a way to amalgamate metals, used mercury as an electrode in an electrolytics process. Um, Emissions from burning waste, incineration of waste was a historically large source of mercury. Not so much anymore, but at one time it was a really big one. Um, all sorts of places, and batteries, fluorescent lamps, thermometers, mercury switches, thermostats. We even used mercury in certain antifungal, anti-fouling paints, like on ships. They would paint the bottom of the vessel with this mercury containing paint to retard the growth of barnacles and whatever animal sea life on the bottom of the ship, these little things that would cause resistance when the ship goes through the water. You don't want barnacles. It uses fuel and it reduces the performance of the ship. So they'd paint it with this stuff to basically make it so the barnacles didn't want to attach to it. That was one source. There's so many different places that people used mercury over the last 1,000 to 2,000 years. We've known of it since antiquity. So the situation basically becomes that all these different sources of mercury, the thing about it, we've got our sample of mercury here, pretty substantial one. This very liquid, and not only liquid, but also relatively volatile metal. So in its metallic form, it's pretty inert, but it's volatile. So it will evaporate. As far as metals go, it evaporates easily. And that allows it to get to the atmosphere, and then it can mix into the atmosphere, and then chemistry can happen over time, converts it into mercury salts, like mercury bromide, mercury chloride. Then those salts get washed out of the atmosphere with precipitation. Then they end up in surface waters because those salts are soluble in water. And then bacteria are able to work on that mercury and convert it into methyl mercury. And I don't know if the bacteria are using it as an energy source or what they're or an electron donor or electron acceptor. There's some kind of a process going on here where these bacteria are converting the mercury to an organic version of mercury. So methyl mercury. The thing with methyl mercury is then it becomes fat soluble. And here's where it rises up the food chain. So if you got a fish, or you got plankton, or you got these little microscopic kind of animals going on here, zooplankton, the methyl mercury builds up in their fatty tissues. And then smaller fish eat that, and as they eat it, the mercury accumulates in the fat, the methyl mercury, because their excretory system isn't going out and scavenging the mercury out of the fat tissue. The mercury just kind of builds up in there. Then the tuna or big fish eat the smaller fish, and then you've got this accumulation effect as it goes up the food chain. Next thing you know, what became parts per trillion, whatever levels of mercury, accumulate at higher concentrations in these larger organisms, these big fish. And then us human beings put our nets down and we gather some of them up and we pack them into cans and then we get them in the grocery store. And that's how it happens. The most interesting part to me is the sources of this mercury, right? We see there's a volcano pictured on this graphic here. You know, it's people might be like, oh, it's volcanic source. It's natural. There's nothing we can do about it. It's no big deal, you know, and all that, you know, the typical response to the calls that there might be an environmental problem here that human beings are responsible for. We get this sort of reaction, well, it's all natural. It's no big deal. Like, all right. Well, actually, only 1/3 of the mercury that is emitted into the environment is from natural sources. Volcanic activity, wildfires, and weathering of rocks. So, reason that volcanoes and wildfires are implicated is because they're hot. So mercury, as I said, is volatile. Even at room temperature, it vaporizes appreciably. We could measure mercury vapor coming off of this container if I was to open it up. It would be noticeable. If the container were filled with a chunk of lead, you're not going to detect lead vapor coming off of that, right? Lead is not volatile. Mercury is. And mercury is especially volatile at the temperatures of a volcano, say 1200 degrees Celsius or something of that along those lines. Even of a wildfire, which could be in the hundreds of degrees Celsius. And it heats up mercury atoms that are either in the soils or in the biomass that's burning. Okay, you don't have to have that many mercury atoms in a forest when you're burning thousands and thousands and thousands of tons of material. It becomes an appreciable amount of mercury. Same thing with a volcanic eruption where you're heating, you've got millions of tons possibly exposed at high temperature, releasing volatile materials. But where do humans come into play, right? Because I said only 1/3 of the mercury is attributed to natural sources. Well, a lot of different ways. Number one, what is this stuff? Coal. Right? Human beings, how much coal do we burn? Around the world, we're burning around something like 7 billion tons per year. 7 billion tons per year. In the United States, we're down from the peak of it in 2008 was about 1.5 billion tons. Now we're down to about 500 million tons per year of coal in the US that we burn. So there's not a whole lot of mercury in this coal. If I was to analyze this and determine the elemental composition of the entirety of it, mercury is not going to be high on the list of elements that we find, right? But I said we burn 7 billion tons of it. So even at a low concentration, it becomes a substantial amount. Your typical coal-fired power plant in the US is emitting somewhere, gets 50 kilograms per year, something like that, which comes out to a little over 100 pounds of mercury. And of course, there's technology that we can apply to minimize that emission. One of the really interesting things is over the past 15 to 20 years is the number one, the use of coal has dropped in the, just say the United States, but also the power plants that we have left that are remaining burning coal are much, 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 much cleaner in terms of pollutants like mercury than the ones that were operating 20 years ago. So between the situation where regulations came into effect that told the industry that, hey, you need to cut back on how much mercury you're emitting into the atmosphere. They call it the MATS rule, Mercury and Air Toxic Standard. That was one thing, and it required the power plants to do something to control emissions. And there were, of course, like every environmental regulation, there were groups of plants that were in the rule, and there were groups of plants that were exempted, and there were different tiers depending upon the type of fuel being burned and size of the plant and all those different aspects of industrial regulation. Anybody who has been around it knows what I'm talking about. There are exemptions and different classifications for everything. So the situation is that we have cleaner plants running because all the old inefficient power plants that didn't have the pollution control equipment mostly were closed because of the transition to natural gas for electricity generation in the United States. But the plants that remained open were upgraded, if necessary, to meet the MATS standard. The owners of those plants saw that it was economically feasible for them to just upgrade it and keep running versus just shutting the plant down and using gas or using some other energy source to produce electricity. So coal, I think they say, is about 45% of the anthropogenic mercury emissions. Where's the rest come from? Well, there's a whole big list. The one source that used to be very significant was incineration. Okay, we have this is the furnace grate of a municipal waste incinerator. Basically, they have these great bars, and the garbage kind of tumbles down like a staircase, and air shoots out through these little holes, and it burns it. And this thing here is, what do we notice? It's hot. Therefore, if there's mercury in that waste, it's turned into a gas. It's vaporized. and it goes up into the exhaust and has to be managed somehow, or else it's going to hit the atmosphere. So basically, two things happened here. Or no, three things happened here with waste incineration. Number one, we don't incinerate nearly as much waste. Well, I shouldn't say this. That's not true. I'm thinking United States. Around the world, we have increased the prevalence of, I'm calling it incineration, but it's waste to energy plants. We're using it as an energy recovery system. But around the world, we have increased the number of tons of waste that's combusted, but we've reduced the quantity of mercury in that waste substantially. We're not throwing away thermometers and thermostats and mercury containing paint and switches and things like that anymore into our batteries. There's another one. Mercury is not in batteries anymore. Used to be like all your AA's, and there was a coating of mercury inside of the cell that protected the zinc from excessive corrosion. We don't have that product anymore. So if that stuff ends up here, you're not going to be creating mercury emissions. The other thing is these plants were mandated to control mercury emissions. So they have some form of removal, often in the form of they blow activated carbon into the exhaust gas before it hits the filter system, and that absorbs or adsorbs the mercury. And then that mercury then becomes part of the ash that is removed and disposed of in a secure location. So we don't have that mercury being discharged into the atmosphere. Another source of mercury that is probably a little startling to many of us, but it is these guys, the old silver fillings, right? So this was about 50% mercury. So in order to pack the filling into the tooth, they had to have something that was almost like a Play-Doh consistency. So they would basically take liquid mercury, and they would mix it with silver or tin or copper or some combination of those, and it would form an amalgam. They'd be soft and pliable for a while. They'd put it in here, and it would kind of, over time, solidify, and you'd have a metallic formed fitting or filling, right? And studies and studies and studies have been done on these, and they determined that, yeah, we can detect mercury atoms coming off of these, but it's not enough to be deemed a health hazard. Although my dentist doesn't use these anymore. I don't think most dentists use them anymore because they have regulatory requirements, number one, that tell them that if they pack this stuff into people's teeth, they need to control all of the particulate matter. So when they drill it and they polish it, they need to capture all of that dust and debris that comes from that process. If you remove one of these, you have to capture all the mercury. It can't just be allowed to flow down the drain, because what happens? It finds its way to the sewer system, and then it finds its way into the sewage treatment plants and ends up in the environment in one way or another. So dentists' offices are mandated to control the discharge of these amalgams if they're still dealing with them in certain amounts. What's the other problem with this? Of course, eventually every person passes away, right? Where happens to the mercury that's in their teeth? Well, it depends, okay? If you choose cremation, what are we talking about again? It's hot. The mercury is volatilized. And of course, crematoria do not have, at least in the United States, are not controlling mercury emissions. That stuff just goes right up the stack. there's no filters, or the governments in the United States do not mandate that they control emissions of mercury. Now, in some countries in Europe, there are regulations that mandate crematoria to control mercury emissions. So basically what they're doing is they're doing the same thing as the incinerators do. They collect the gases, they cool them down, they blow activated carbon into the stream, and then they filter that carbon out before it goes up the stack, and then all the mercury is in the carbon that is disposed of probably at a hazardous waste land disposal location, something like that. So, those are kind of the sources that are common from combusting things. But what about this stuff? This is a more historical source of mercury. We've got ourselves some bleach, sodium hypochlorite. What does that have to do with mercury? Well, you can look this up online. I don't have a graphic here, but they would use mercury. We're talking, historically. There might even be a few places out there in the world that still run these, but to produce chlorine, you use electricity to split sodium and chlorine apart from salt. So they put salt water into a tank, and there is electrodes in that tank, and electricity goes through there, and at the positive electrode you get chlorine, and at the negative electrode you get sodium. And they designed these vessels, what was called a mercury cell, where the negative electrode was made out of liquid mercury at the bottom of the tank. And what would happen is the electricity would be applied to that mercury, and the sodium ions would go into the mercury, and they'd form a sodium amalgam, basically an alloy, just like the tooth filling, of mercury and sodium. Then they'd put that sodium amalgam into another tank, and it would react with water, and then they would create sodium hydroxide, and then the mercury would go back to elemental mercury just by itself, and then they'd recycle the mercury. Well, the problem was that a small quantity of mercury would always be left in the wastewater, and that at the beginning was discharged to the environment. And that's how we had things like Minamata disease in Japan, because these plants that were using these mercury cells were discharging the mercury in small amounts, and we were doing a localized extreme version of this in Minamata Bay, and people were eating these fish, and they got acute, deadly levels of mercury exposure over, some number of years. So mercury cells were used to produce chlorine. Now we've switched to things called diaphragm cells and membrane cells. Membrane cells being the best of the best of technology to produce chlorine. We don't need mercury anymore, right? We don't need mercury switches anymore in thermostats, and it used to even be so common for the trunk of a car. You'd lift the trunk lid. What happens? The light comes on. Well, how'd they do that? Magic, right? No, it's a mercury switch. There was a little tube with a bead of mercury, and when it would tip over, with the lid being opened, it would create an electrical circuit and turn the light on. Oh, that's great. That's really cool, right? That's a really neat idea. Yeah, it is, except what happens to that car at the end of its life? Goes to the junkyard. What happens? Oh, they crush it. Well, what happens after it's crushed? What happens to steel when you recycle it? This isn't the right picture, but you get the idea. It's hot. It goes in an electric arc furnace, and they melt it. What happens to the mercury? Right to the atmosphere. Right? So that is how mercury ends up in your tuna. Number one, humans thought mercury was a really, really, really good thing to use for a lot of stuff. Hey, it's really useful, right? What's the other thing that human beings are fascinated with? Fire. We are pyromaniacs. I said, we burn 7 billion tons of coal every year. We burn garbage to get rid of it. We even burn people to get rid of them after they've died. Right? Humans are obsessed with burning things. And if there's mercury in the thing that you're burning, where's it going? It's going into the sky. Unless you have some kind of technology to capture it before that happens. We make cement. How do we make cement? We take coal and we take rocks and we heat them up to really, really high temperatures. Voila! Burning things. It all comes down to that, right? That is how most of this mercury ends up in your fish. Just like the volcano. It's heat volatilizes it. It goes to the atmosphere. It rains out as a salt or whatever compound. Bacteria convert it into methyl mercury. Then the methyl mercury accumulates in the fat tissue all the way up the food chain to ends up at the tuna, which ends up at the grocery store in the cans, and it says on the can that our tuna has less mercury than their tuna, and that's the story. And that's it.